Hello, my name is Shyam Iyer. I'm a distinguished engineer at Dell, but here I'm in the capacity of the chair of a newly formed technical work group inside SNIA called SDXI. And I'm here to present to you a new path to better data movement within system memory and computational memory with SDXI. What is SDXI? SDXI stands for Smart Data Acceleration Interface. It's a proposed SNIA standard for a memory-to-memory data mover interface. So let's look at the agenda. I'm going to talk to you about the problem and the need for a solution. And then I would introduce SDXI and how it can solve the problem. So to understand the problem, we have to understand some of the system design challenges that we see today. So core counts have been increasing to enable compute scaling. And that's generally a good thing because we need to run lots of applications, lots of VMs, and our CPU vendors have been very good here. Compute density is on the rise, which means now you can pack a lot of applications or VMs on the same systems. Hyperconverged and converged storage appliances are now enabling new workloads on server class systems, where data locality is very important. And that has generally improved performance for our applications. But we also see that single-threaded performance is now under pressure. And that lends itself to different kinds of system design challenges. We also see that IO-intensive workloads can now chip away at your chargeable CPU cycles that are available to you. Some examples for that are like network and storage workloads that can take away some of your CPU cycles. And then things like data movement, encryption, decryption, and compression, they all can take away from the application performance. To draw an analogy to this, you can look at the picture here where the single-threaded performance is a car that is going fast on its lane. So you can build a very fast car, but you're still running in that same car. So, you're getting a finite performance limit with that. Now you can scale it with multiple cores, like you have multiple lanes here and you can run multiple cars through that. But, if you have that bus going through in between, and that's kind of like some of your IO intensive workloads, that can still cause bottlenecks, no matter how many lanes that you build or how many fast cars that you have. Also important to see here is there are some trapped resources out there that look at the car over there, it's trapped and it's not moving. We need to unlock some of these trapped resources from our system as well. And these are the ways that we want to solve some of the system design challenges. And to understand how an application performance bottleneck can build up, so if you want to run some applications, then you would run it on a compute platform, a host or a hypervisor. And you can generally scale that using network stacks that are built for the application. Now you need storage for this as well. So to get storage, you could get that from the same host, you can go to a storage stack on a storage VM that the same host provides. And if you see here, the local storage that the host can provide has been generally improving. And it's been improving the performance. So now we have non-volatile memory express, and then new persistent memory technologies starting with NVDIMM that are reducing the latency envelope and then increasing the capacity at the local storage quite effectively. And then if you didn't want local storage and you want some kind of a remote storage that the host can provide, then you can use a storage cluster network and get some of your storage needs met. And here as well, we've been doing pretty well, which is we've been adding TCP/IP, Rocky, IVARP, and then the latency has been improving, and the speeds and feeds have been improving with 10 gig, 25 gig, 40 gig, 100 gig, and beyond Ethernet networks. And then the IO interconnects that are enabling some of these technologies are also been improving with PCIe and then CXL and then Gen Z as well. So you can see that there is the bottleneck building up at the host. And generally, intra-host exchange is done using software stacks, and then hardware copies is done usually using kernel to IO or IO specific hardware memory copy. But software to software copies relies on CPU only synchronous software stacks, and that's where we see some of the intra-host workload congestion buildup. And if you wanted to solve this problem with like disaggregated host stacks, then you can do this by, let's say your application runs on a specific compute stack running on host hypervisor, and you can scale like before in the previous picture using network stacks, the application demands. But then the storage could also now run on a separate host stack, and then now you have disaggregated those compute and storage stacks using the picture that I'm showing here. But if you see, the same kind of design challenges will apply on both of these host stacks, whether they are for the network side or for the local storage that is being provided in this architecture. And we need to solve the same kind of problems everywhere. So let me look at what is our current memory-to-memory data movement standard. So our current data movement standard is a CPU instruction set architecture through which a software can do memory copies. Now, this is good because a stable CPU set instruction architecture allows for a stable application programming interface. But it can take away from the application performance that like we have talked right now. But there are good features there as well. We can isolate different applications from interfering with each other's data that the software can provide, but that can also add overhead into the software layers. When you have a synchronous software copy operation happening, that can stall the applications from doing anything more useful with the CPU. And then it's less portable to different instruction set architectures, which means that finely tuned CPU data movement algorithms can now break with new microarchitectures. So what do we do about this? We can offload the DMA engines. Is that really a new concept? If you look around in the industry, there are lots of DMA offload engines available, but they tend to be very vendor specific hardware, vendor specific drivers, APIs. They have specific work submission and completion models, which means that direct access by user level software can become very vendor dependent and difficult. And because of this, there are limited usage models in which you can integrate them, and you have to do the same thing with another vendor for a different usage model. So that also causes like vendor specific DMA states, which means you don't know when the DMA operation is before you decided that you wanted to migrate that work to the other host. That makes it very hard to abstract and virtualize these type of offload engines. So what kind of solution requirements we see emerging? We see that we need to certainly offload IO from the compute CPU cycles, but we need to do it in a way that we get architectural stability. Just like CPU instructions provide the architectural stability for a programming interface for an application, we need the same thing from an offload interface. We want to enable applications and VM acceleration, but we want help migration from, we want to help them migrate from their existing software stacks. So to do that, we can do that in two ways. One is we can create abstractions in the control path for scale and management, but we can enable performance in the data path with offloads very surgically. So you get the best of both worlds. And we see a picture emerging for an industry standard that needs to look at various elements in the system design. So for example, if I have one or more than one application, I have been building software context isolation layers in between them, and I've been using the CPU for my data copy. A logical way for me to put an accelerator would be on the CPU in such a way that it doesn't use the CPU cycles, but it provides me the acceleration that I need for data movement from, let's say, a DRAM context A to DRAM context B. But in doing so, I want the same user level access that applications have with the CPU. So I want direct user mode access. and while eliminating the isolation layers. And then if you see, I don't want to do the same investment multiple times on different CPU instruction set architectures or families. I want software to be portable that way. And the accelerator interface, if you see, there are lots of I/O devices like GPUs, FPGAs, smart NICs, smart drives that have a lot of acceleration functions in them. And it would be a nice thing for all of them to have the same interface so that now we can leverage a standard and then innovate around the spec and add incremental data acceleration features. And in doing so, we don't want to restrict ourselves to data movement and acceleration in the DRAM memory space. We also want to expand to different tiers of memory on this, whether they are storage class memory or memory behind I/O devices, or memory attached to CXL links and fabric links like Gen Z. So why focus on standardizing this memory-to-memory data interface? If you really closely study the host application performance, much of the gains it gets is with the data in use. And if you see a common system, the data in use is mostly using DRAM for its performance. If you look at this picture here, the industry has been doing a great job of how to expand the data in use with things like memory expansion with CXL, or putting like large blocks of memory behind I/O devices, or persistent memory now that has been made part of the system physical address space. All of these things are now expanding the envelope for the data in use that can be used by an application. Now, when you see the trends where the heterogeneous compute resource usage is on the rise, all of them can benefit from the data in use model that is expanding. And this also means that the blurring boundaries between a server and a storage host, the same kind of system design principles can be applied in both cases. Because we are also accelerating disaggregation, this can unlock trapped resources using a standard method. So a memory-to-memory interface can do three things to the industry. It can become a computational memory interface, because now you can do computation with it. And then it can also become an interface to accelerate storage and memory convergence. And then the third thing it can do is it can be an interface to accelerate resource disaggregation with memory links that connect them or fabrics that connect them from a memory-to-memory data movement perspective. So with that, I would like to now introduce SDXI and some of the concepts behind SDXI. As I said before, SDXI stands for a Smart Data Acceleration Interface. It's a memory-to-memory data movement and acceleration interface. So a good way to think about some of the design tenets of a memory-to-memory data mover interface is, it's built of multiple PFs and multiple VFs that can provide some of the context isolation layers between various applications or VMs that are in the host. And it can do data movement between them both within and across VMs. Such a data mover implementation, we envision that it is independent of the actual implementations behind it, and also the I/O interconnect that is used to do the actual data movement. And then the data movement needs to happen without mediation by like privileged software, like hypervisor. But at the same time, we want that to be easily abstractable or virtualizable by privileged software. And when we do that, now we allow live workload or virtual machine migration between servers. And we also want this DMA model to be concurrent, which means that one DMA should not stop other DMAs, and multiple DMAs should happen at the same time. And because we are building a standard, we want forward and backward compatibility for software and hardware. And this means that now we can incorporate additional offloads in the future with that same interface. So as you would imagine, a well-behaved and well-designed standard it looks at hardware, and we look at hardware built using multiple functions, like I mentioned, either a PF or a VF, and the function space has some MMIO addresses, spaces that you can program, and we define a concept called context, where it's managed. It manages the state of the context that is used to submit work to the SDXI function, and the context points to a descriptor ring where you can insert your work, and the work can now be managed using read indexes and write indexes between the hardware, software, or the producer and the SDXI function. And we can use things like doorbell to tell the SDXI function that there's new work. As you can see, all of these context states reside in memory. And then we rely on a standard descriptor format and a function setup and control that is accelerator independent, which is a big thing. Making it simple, making it standard will get us there. And it's very easy to virtualize, and that's one of the reasons that this makes it so useful. And we can also do things like the ring states can be directly managed by user mode applications. So while a privileged software can control how the contexts need to be managed and created, the user mode can directly use a descriptor ring and then submit work to the SDXI function. And then there is one way to set up control and quiesce context, which is very important when we want to migrate the work from one host to the other host. And then there's one flexible way to log the errors. And so you can see that we're putting some good thought around how exactly an accelerator should behave. And like I mentioned, we're building a standard descriptor format, which can be used for different types of operations. And we're doing some groupings in a logical way, where there's certain kinds of operation groups and specific operations within those operation groups. And when the operation kind of completes, we get a completion signal back from the SDXI function in a very standard way. As you can see, there's a lot of room for future operations that can be defined with this interface. And we expect the spec to grow based on that. I will walk you through a specific example of rep copy. And as you have already guessed, a rep copy is repeat copy, and it can be a very useful tool for a host to perform some of its functions. So for example, a host can have a kernel application or a hypervisor application that wants to start a VM. And before starting the VM, it needs to initialize a large buffer memory space with just zeros, right? So that's a simple operation, but if you wanted to use your CPUs to do that, that can take away from the application performance that the host is running there. So an SDXI device can come to the rescue, and then it can take a small source buffer filled with a pattern, and then repeat the same pattern and write it into to the destination buffer space. And this becomes quickly a powerful tool of how you have done a computation on the memory of just filling the memory buffer space with zeros. So how can this be more useful? It's not just for kernel mode application. So while we think a kernel mode driver can initialize and discover the capabilities from the hardware to do the initial setup, it can now enable like a kernel mode application, like in the previous example with a producer ring to perform some of the data manipulation operations that it needs to perform. And then it can also enable, using an OS-specific interface, a user mode driver or a library that can now, in turn, enable specific applications with their own descriptor rings that can directly submit work to the hardware without having to, build too many software layers in between. And if we want to truly, scale the data in use memory address space, then, like we talked about, this works with DRAM or persistent memory or memory behind I/O devices, or the CXL address space, and the user mode applications can benefit from that. We also think that because various applications perform in different address spaces, this user mode application A can now do the data copy between its address space to the address space B. And this is a bare metal stack view of how this could be useful. And you can see that this can be scaled with compute virtualization. So a hypervisor kernel mode driver can perform the same initial functions of discovery and capabilities. And then it can now enable one or more VMs with a virtual SDXI device. Now the virtual SDXI device could have a guest kernel mode driver that can enable kernel mode applications and user mode applications like in the bare metal use case. And now we can, using the connection manager, we can set up two VMs to talk with each other. And then you could have a kernel mode application on VM A do data transfers to the kernel mode application on VM B, or a user mode application on VM A can now do data transfer with user mode applications on VM B. So as you can see, this is a powerful concept, and we started this technical work group in SNIA last year in July. The technical work group had its first meeting in July, and since then we have met every week to discuss the specification. To start the work on the specification, AMD, Dell, and VMware contributed the initial version 0.7 draft specification as a starting point. And then very quickly, 22 plus companies and over 50 individual members have joined this group, and we're still growing. So with all the companies joining in the review process, we are pleased to inform that we finished our initial review of all the things that the spec could improve for a version 1.0, and we are in the process of implementing them. And then we are also working on building OS-independent software reference code, and this would help compliant implementations to look at a reference implementation and benefit from it. As you can see, we have a list of work that we want to do this year, and we are also collaborating with other SNIA groups around persistent memory and the computational storage work group, because collaboration here is going to be important to move the industry forward, and that includes collaboration with PCI SIG, CXL, and Gen Z. So what will we do focus post 1.0? So we think that because this is an extensible spec, we can now add new data mover operations for acceleration. We can involve data movement operations where we are targeting persistent memory. Then we can now build efficient cache coherency models that involve these type of data movers. And when you do this, we think security is very, very important, and we can build certain kind of security features that involve these type of data movers. And then, like I said, a connection management architecture is important when you're talking with multiple address spaces. And we would be focusing on standardizing them as well. We are encouraging adopting companies to work towards compliant implementations and driver models. And we are very pleased with all the support that we are getting from the OS hypervisor vendors, the OEMs, and the acceleration vendors. As I mentioned before, we are a good group. So we're a fun group, and we've got a lot of companies, relevant companies in this space that have already joined, but a standard needs the help and work, collaboration of all the people, which is what we're doing here. So please come and join us in the twig and help us improve this. So how can you get involved? You can reach us through the standard SNIA channels. If you don't want to join the technical work group, you can still participate in a public review of the draft specification that is showing up soon. And then if you want more details on SDXI, we did a couple of presentations. There are some YouTube links for this. And then if you have questions, I would be happy to answer them over email as well. And then last but not the least, the SDXI technical work group is a very close group. And a lot of members have contributed to the specification, and I want to thank them all for all the time and effort that they're putting every week and after meetings as well to make the spec a good spec that everyone can implement. And I would like to also thank the conference organizers for the opportunity to present this. I look forward to all your questions in chat, and love interacting, and hopefully next time we could be face to face in our conversation. Thank you.